Good morning, dear students. Welcome back to physics class. Today, I am going to discuss on the following topics: A. Motion in a plane with constant acceleration. B. Relative velocity in two dimensions. And C. Related numerical part B. In the first session of today's class, I am going to discuss on this part motion of an object in a plane with constant acceleration. Consider an object is moving in xy plane and its acceleration a is constant. Over an interval of time, the average acceleration also will be constant value. Now, let the velocity of the same object be v0 at time t is equal to 0 and v at time t. Then by definition, the average acceleration is the rate of change of velocity, which can be mathematically written as a is equal to v minus v0 by t minus 0, which is equal to v minus v0 whole divided by t, or v is equal to v0 plus at, which is the expression 1a. In terms of component, how can we write the expression 1a, which can be mathematically written as vx is equal to v0x plus axt and vy is equal to v0y plus ayt. These expressions are represented by the number 2. How should be the position change with respect to time? To understand this, you have to consider one-dimensional motion of the same object and apply the same method used in this case for the two-dimensional motion. Let r0 and r be the position vectors of the same object at the time t is equal to 0 and time t is equal to t. And let the velocities at this instance of time be v0 and v. Then over this time interval t, the average velocity is the arithmetic mean of initial velocity and final velocity, which is equal to v0 plus v whole divided by 2. Then what should be the displacement of the object, which is equal to average velocity multiplied by the time interval, which is r minus r0 is equal to v0 plus v whole divided by 2 into t is equal to v0 plus at whole divided by 2 into t, since v is equal to v0 plus at. This is equal to v0t plus half at square. You should remember that when an object is in uniform acceleration, its average velocity should be the arithmetic mean of initial and final velocities. So, the expression becomes as r is equal to r0 plus v0t plus half at square. Then r minus r0 is equal to v0t plus half at square, which is the expression 2a. When you differentiate the expression 2a with respect to the time t, you get the expression 1a, which is v is equal to v0 plus at. Then d by dt of r minus r0 is equal to v is equal to d by dt of v0t plus half at square is equal to d by dt of v0t plus d by dt of 1 by 2 at square is equal to v0 into d by dt plus a into 1 by 2 into d by dt of t square is equal to v0 into 1 plus 1 by 2 into a into 2 into t into dt by dt is equal to v0 plus at, which is the similar expression. The expression 2a satisfies the condition that at a time t is equal to 0, position vector r is equal to r0. You should notice that change in position vector of an object is its displacement vector. The expression 2a can be written in its component forms as x is equal to x0 plus v0 xt plus half ax t square and y is equal to y0 plus v0 yt plus half a yt square. These are the expressions 2. From these expressions, it is seen that motion in a plane, that is two-dimensional motion, can be treated as two separate simultaneous one-dimensional motions with constant acceleration along two perpendicular directions, which are x and y directions. These two directions are independent of each other. Consider two objects moving in straight line. The velocity of one object relative to second object is called its relative velocity. The second object might be moving slowly, moving with the same velocity, moving with a higher velocity, or moving in opposite direction or stationary. Whatever state might be, if initial positions of two objects A and B are xa0 and xb0, their positions at the time t will be xat is equal to xa0 plus vat and xbt is equal to xb0 plus vbt. Then the displacement from the object A to the object B can be written as xbt minus xat is equal to xb0 plus vbt minus of xa0 plus vat, which is equal to xb0 minus xa0 plus vb minus va into t. Then how can write the velocity of B relative to A and velocity of A relative to B? These are in the form of the relative velocities. We can write them as velocity of B with respect to A or relative to A is equal to VBA is equal to VB minus VA, and velocity of A relative to B is equal to VAB is equal to VA minus VB. Earlier, I had pointed out to you that the concept of relative velocity in one-dimensional motion can be applied to two-dimensional or three-dimensional motion. Suppose that two objects A and B are moving with velocities VA and VB, each one with respect to some common frame of reference, say ground. Then the velocity of the object A relative to that of B is equal to VAB is equal to VA minus VB, and similarly the velocity of the object B relative to that of A is written as VBA is equal to VB minus VA. Therefore, VAB is equal to minus of VBA. Even though these relative velocities are in opposite directions, their magnitudes are same. So, mod or modulus of VAB is equal to modulus of VBA. Examine the numerical part. Question 1. Rain is falling vertically with a speed of 30 meter per second. A woman rides a bicycle with a speed of 10 meter per second in north to south direction. What is the direction in which she should hold her umbrella? The described situation is shown in given figure. Given that VW, which is velocity of the woman towards the south direction, is equal to 10 meter per second, and VR, which is velocity of falling rain, which is in vertical downward direction, is equal to 10 meter per second. Since VW is towards the south direction, then minus VW should be towards the north direction, which is shown in given figure. In order to protect herself from the rain, the woman must hold her umbrella in the direction of the relative velocity, that is, the velocity of the rain with respect to the velocity of women, which is VRW. As shown in given figure, VRW is equal to VR minus VW, which is also obtained by using the triangle rule. Then velocity of the rainfall relative to the velocity of the women is written as VRW is equal to VR minus VW is equal to 30 meter per second minus 10 meter per second is equal to 20 meter per second. Then, in what direction should she hold her umbrella in order to protect herself from the rain, which is obtained by using tan theta is equal to opposite side divided by adjacent side of shown right triangle is equal to VW divided by VR is equal to 10 by 30 is equal to 1 by 3. Then theta is equal to tan inverse 1 by 3 is equal to 18 degree 26 minute. Hence, the woman must hold her umbrella towards the south direction at an angle of nearly 18 degree with the vertical. A man can swim with a speed of 4 km per hour in still water. How long does he take to cross a river 1.0 km wide if the river flows steadily at 3 km per hour and he makes his strokes normal to the river current? How far down the river does he go when he reaches the other bank? The situation from the given question is shown in the figure. Given that speed of the man Vm is equal to 4 km per hour, width of the river is equal to 1 km. Then what should be the time taken by the man to cross the river, which is T is equal to distance divided by speed is equal to width of the river divided by speed of the man is equal to 1 km divided by 4 km per hour is equal to 1 by 4 hour. And also given that speed of the river VR is equal to 3 km per hour, then the distance covered with the flow of the river is equal to speed into time is equal to 3 km per hour into 1 by 4 hour is equal to 3 by 4 km is equal to 750 meter. And third question is, in a harbor, wind is blowing at the speed of 72 km per hour and the flag on the mast of a boat anchored in the harbor flutters along the any direction. If the boat starts moving at a speed of 51 km per hour to the north direction, what is the direction of the flag on the mast of the boat? Given that velocity of the boat Vb is equal to 51 km per hour and velocity of the wind Vw is equal to 72 km per hour. As the flag is fluttering in the northeast direction, then the wind should be blowing towards the same direction. That is, it is towards the northeast direction. When the ship begins sailing towards the north, the flag will move along the direction of relative velocity of the wind with respect to the boat. Let VWB be the relative velocity of the wind with respect to the boat. Then, what should be the angle between VW and minus VB, which is shown in given figure? It is equal to 90 plus 45 degree. Let beta be the angle between VW and VWB. The angle beta because beta gives the direction of the flag on the mast of the boat. So, what should be tan beta? Tan beta is equal to B sin theta divided by A plus B cos theta. Here, A as 72 km per hour, B as 51 km per hour and theta is 90 degree plus 45 degree is equal to 135 degree. Then tan beta is equal to 51 sin 90 plus 45 divided by 72 plus 51 cos 90 plus 45, which is equal to 51 cos 45 divided by 72 plus 51 minus sin 45. Since sin 90 plus theta is equal to cos theta, then sin 90 plus 45 degree is equal to cos 45. And since cos 90 plus theta is equal to minus sin theta, then cos 90 plus 45 degree is equal to minus sin 45 degree. So, it will be equal to 51 into 1 by root 2 whole divided by 72 minus 51 into 1 by root 2 as cos 45 degree is equal to 1 by root 2 and sin 45 degree is equal to 1 by root 2. This gives to 1.0038. Then beta is equal to tan inverse 1.0038 is equal to 45.11 degree. As beta is the angle between the wind and the relative velocity VWB, which is the velocity of wind with respect to the boat, then what should be the angle made by the direction of wind with respect to east direction, which is 45.11 degree minus 45 degree is equal to 0.11 degree. This gives the direction of the flag on the mast of the boat. Hence, the flag will flutter almost due east. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.